So we've looked at solving linear systems with graphing, with algebraic methods of elimination and substitution. However, most of the time in your life, you're not likely to be walking down the street and just happen to find a pair of equations laying on the ground that you need to solve. So we need to be able to use these more effectively, such as making mathematical models from problems. So we're going to look at a few problem types. We've already done some problems with these, but we're going to look at some special problem types that we regularly encounter and look at the procedure that we use when we encounter these types of problems. The method you use to solve them, really, it depends on the situation. In most cases, the algebraic methods are going to be best. You can use substitution and elimination and get an accurate answer without having to do much in terms of drawing and whatnot. However, if there's, you're going to get whole number answers, and there's a visual, using a graph, a visual of the situation is going to be beneficial. Like if you're trying to describe a situation to your bosses in a presentation or something, then maybe graphing would be good. But in most cases, algebra, doing these by hand is the quickest way. Technology-wise, you can do both in equal speed. So let's look at some money problems first. So a lot of times we're going to have questions where we're selling items, two different items, and we'll know how many we sold and what the amount we made was, but we won't know, how many of each did we sell, or maybe conversely what the price of them was. So that's this type of problem we're going to take a look at. So in this question here, we got Dean and Fitz selling cupcakes for a fundraiser. They're selling large cupcakes at $3 each and small cupcakes for $2 each. In this case, they sold 180 cupcakes, made $440. We want to know how much they sold of each one. So again, we need to model this with some algebraic equations. We have the 180 cupcakes that we sold, the $140 that we made, and then we know the cost of the cupcakes. We don't know how many. So let's pick some things to make variables. If we don't know how many of each size they are, those are the variables. So we got some large cupcakes. I'll use a capital L for that. That'll be the number of large cupcakes. And then a capital S is the number of small cupcakes. If you write your S's and they look like 5s, feel free to use other letters. It doesn't matter the letters. It's just there for a placeholder variable. And then we need to make a couple equations. So our equations here, we have the number of cupcakes sold is 180. So the number of large plus the number of small should be 180. So L plus S. Go a little better. There you go, my S looks like a 5. S equals 180. And then they made $440. Well, the cost of the large cupcakes, or the money they made from the large cupcakes, is $3 times L. So 3L plus, and then the $2 per small cupcake, so 2 times the number of small cupcakes they sold, equals 440. So there's two equations, two unknowns. This one here works out well for either solving by substitution if we rearrange the first equation, or solving by elimination. Let's do substitution on this one. So we're going to rearrange 1. And we're just going to take the L and throw it over in the other side. We'll have S equals 180 minus L. So that's 1 rearranged. Now we can sub 1 into 2, and we'll get 3L plus 2 times 180 minus L equals 440. Expand that out, 3L plus 360 minus 2 equals 440. Sorry, 2L. We're left with L equals 440 minus 360. And L equals 80. So we had 80 large cupcakes, and then we'll just sub that into the rearranged equation 1. So L equals 80 into 1, and we're left with S equals 180 minus 80. S equals 100. So we got 80 large cupcakes, 100 small cupcakes. Before they sold, 80 large and 100 small cupcakes. So we've done similar questions to this one, but again, every time you get a question where you have the cost and number of items, you're going to be setting it up like this. Generally, we're going to be looking for the number of items, so we set those as our variables, and then the total number of items was the sum of those two numbers, and then we can multiply the individual costs by the number sold to get the total value. So a common type of question that you'll see is this, and that's the general solution to those types of questions. Another common type of question is working with distance, speed, and time, especially if you're moving with a plane or a boat where you have some resistance, be it wind resistance or water resistance. So if you're working with tailwind and headwind in terms of a plane, in terms of tailwind, if I draw a little plane here, so here's my plane. A tailwind means it's pushing on the tail. So that means it's pushing the plane faster. A headwind would push on the head of the plane. And make the plane go slower. Okay. So whenever you hear the term tailwind, it means it's pushing from behind and making it go faster. Headwind is going to make it go slower. Now, in our situation here, we have a tailwind. With a tailwind, the plane flew the 1,800 kilometers from Saskatoon to Toronto in 3 hours. The return flight against the wind took 4 hours, so it went slower. We want to find the average speed of the plane and the wind speed. So in these types of problems, what we want to do is set up a little table using the knowledge of this equation. Distance equals speed times the time. Okay. Switch that to a lowercase d. More appropriate. So distance is speed times time. You need to memorize that formula, be familiar with it, or be able to calculate it, or rearrange it from speed equals distance over time. But you do need to know that formula. You'll be using that a lot. So if we take a look at our situation then, we're going to make a little table here. We got the direction, the distance, the speed, and the time. So this is our table. These are our three headings. And so our direction is, I'm going to use tailwind. So that's on the way there. Against the wind would then be a headwind. Okay, so I'm going with a tailwind, then I'm going with a headwind. The distance in both cases, as we go from Saskatoon to Toronto and then Toronto to Saskatoon, is going to be the same, 1,800. The speed, we don't know. the times we do. So the time with the tailwind was 3 hours and then 4 hours. Now, this is where it becomes important. We need two variables in these type of questions. We need because we need the speed of the plane and the wind speed. Okay, so we need two variables, the plane and the wind. So our speed is going to be made up of those two pieces, the speed of the plane and the speed of the wind. With the tailwind, it's going to go faster. We're going to add the speed of the wind to the speed of the plane. So we're going to have the plane plus its wind speed because it's going faster. On the way back from Toronto to Saskatoon, the wind made it go slower, so it's going to be the plane speed minus the wind speed. The wind's going to make this overall speed slower. And then we go back to our equation. Distance equals speed times time. So we have our formula. Distance, and then there's our speed and time. We would then take this set of equations and expand them out. So we're going to multiply P and W by 3 in the first one. 3P plus 3W. And then we're going to do the same thing in the second one, multiplying by 4. 1800 equals 4P minus 4W. Now we have two equations that we can go about solving. Here, you may wish to use something like elimination, multiplying the equations by maybe multiply the top one by 4, bottom one by 3 to get an equivalency. Or you may wish to rearrange one and solve by substitution. But once you have your equation, you're going to pick a method of elimination or substitution to solve that. I'm not going to solve it here. If you want me to check, if you want to solve it and me to check your answers, I can do that in class. But just to save some time on the video, because it's getting fairly long as it is, I'm just going to show you how to set up these formulas. And you can refer back to solving by elimination or substitution to solve that. So looking at the next type of problem, we have a mixture problem. So we often get these mixtures. Sometimes they use percentages, sometimes they use weights, sometimes they use volumes. But when we're mixing two things together to get something in between, an in-between mixture. So in this case, we have an alloy of aluminum is 35% aluminum, and another alloy is 55% aluminum. And we want to mix these two together to get 1,000 grams of an aluminum alloy that is 40% aluminum. So these types of questions, it might be mixing high quality coffee with a lower quality coffee to make like a coffee blend, and then figuring out the price of them. So instead of percentages, you could have prices, and figuring out the weight in grams of each of those. It could be mixing like a saline solution and trying to get the certain percentage of saline in the solution, and then we could use percentages again, or it could be finding the volumes of those as well. But in any of these cases, you're taking two different amounts of things and trying to mix them together to get a certain volume or weight and then a percentage mixture. So in this case here, we can set this up again like the last one using a table. So the volume of each solution, and then the amount of 35% aluminum, the amount of 55% aluminum, and then the final mixture, which is 40%. So the percentages become our headings. So the volume of the mixture, or let's better call it an alloy in this case. So in this case, the alloy. So the volume of the alloy, and then the volume, or sorry, mass. This is mass in this case. referring this to as mass. And then the mass of the aluminum itself in each one. Okay, so we're looking for the total mass. So the alloy itself, the alloy mixture, is going to be 1,000 grams. And it's a 40% aluminum mixture. So 40% of 1,000 will be how much aluminum mass is in there. So it's 1,000 grams total, and then the aluminum mixture is 40% of that. It's going to end up being 400, but I'll write out the equation so you see where that 400 comes from. In terms of the 35 and 55%, we need to know how much of each. So what mass of each are we getting? So the mass of the 35%, so for variables, I'm going to do a capital T for the mass of the 35%, and then a capital F for the mass of the 55% aluminum mixture. So this will be the total mass of the 35%, T, and this will be the total mass of the 55%. If we add the mass of 35% plus the mass of the 55%, that will equal the total 1,000 grams. How much of this 35% mixture is aluminum is 0.35 T. 35% of it is aluminum. So that's the mass of aluminum in the mixture. The mass of aluminum in the 55% mixture is 0.55 F. If we add those masses of aluminum together, we'll get the 40% mass we want. This would make our two equations. So if I rewrite these, I'm going to get T plus F equals 1,000, and the second equation will be 0.35 T plus 0.55 F equals 400, which was the 1,000 times 40%. So I have one equation here, I got a second equation here, and then I can use substitution or elimination to solve these. So in the terms of these mixture problems, mass or volume will be the value here. Each percentage mixture, so each of the individual percentages go here, and then the total percentage that we want in the end goes here. We take the mass of the total thing, or in the case of volume, the total volume, add those together, and then we find the percentage of the component. So in this case, a 35% mixture, a 55% mixture, and then a 40% mixture. And we find out the individual masses, in this case of the aluminum. We'll practice with a bunch of these problems, and hopefully that will become a little clearer as you practice. But you do want to make sure you're following the process of making these tables. And again, if you want to try and solve that yourself, and you can check in with me, and I can let you know if you're doing it right.